let's talk about symmetry and how symmetry applies to functions. So I have 3 diagrams drawn here to display different kinds of symmetry. Only 2 of them apply to functions, and I bet you can actually look right now at these diagrams and rule one of them completely out if we're going to be dealing with functions. So, when I look at this one, this is what I call symmetry over the y-axis. And it's a kind of folding symmetry, right? If I take this graph, which I tried to mimic here, and I didn't do the best job ever, but I fold it over on itself, I see the same thing. It lies down on itself, right? It looks the same on the left and right-hand side of the y-axis. Sometimes you'll hear this as symmetry with respect to the y-axis. Well, let's go over here next, because this is what we'd call symmetric with respect to the x-axis, or symmetric over the x-axis. And again, that's a kind of folding symmetry, right, where I fold it over and the graph looks the same on the top and bottom. And this is one that can't be the graph of a function. So I'm not going to care about that if I'm only dealing with functions, because the minute I'm symmetric over the x-axis, we fail the vertical line test. Because that kind of folding symmetry means there's a point here that when I fold it, lines up with a point there. So this one can't be a function. And then finally, we have symmetry with respect to the origin. That's a rotational symmetry. I imagine holding the origin still and rotating 180 degrees. And I notice that my graph looks exactly the same as it used to. That's that origin symmetry. It's a rotational symmetry. And again, it's a 180 degree turn around the origin. So if I'm dealing with functions, these are the only kinds of symmetry that I'll have to deal with. Functions with this kind of symmetry are called even functions. Functions with this kind of symmetry are called odd functions. And what's nice is if we have a picture, it's easy to tell if we're even or odd, have symmetry over the y-axis or symmetry with respect to the origin. There's even an algebraic test for whether a function is even or odd so that we can tell from an equation whether it's even or odd. Because if I know I have an even function, it's going to be easier to graph. Because if I graph half of it, I've automatically graphed the other half just by thinking about reflecting over the y-axis. If I have an odd function, I can do the same thing, right? Because if I graph this part, I know the part down here has to look exactly the same. Well, the way the algebraic test works is by looking at points. So let's say I had a point here at A, and that comes up here, and there's a y value here called f of A. Well, if I come over here the same distance, that would be minus A, right? And there'd be a point up here that also had that same y value, right? Because they fold over on each other. So I could write that down and express it as f of A equals f of minus A. And then I realized there was nothing special about calling that an A, right? It was just a x value, so I'm really saying that f of minus x is always equal to f of x. That if I change the sign on an x value, nothing happens. That's going to be the algebraic test for a even function. For the odd functions, if I have a point over here, there's a y value up here, and over here at minus a, I go down instead of up. And so f of minus a isn't the same as f of a. It's the opposite. And what I realized is that opposite could go on either side. So f of minus x is equal to minus f of x. So if I change the x value sign, I change the y value sign because these y values are opposites. And when I derived it here, I was kind of thinking about the minus here, but if I multiply both sides by minus 1, well, it can go on this side as well. So what I realized is the algebraic test is to evaluate f of minus x and see what happens. If you get the same function you started with no change, that's an even function. If you get exactly the opposite function that you started with, that's an odd function. So I've written those two statements down here. A function is called even if f of minus x is equal to f of x. You replace x with minus x and nothing happens. A function is called odd if f of minus x is equal to minus f of x. You replace x with minus x and you get the exact opposite thing that you started with. So I have 4 examples where I want to determine from just the equations whether the functions are even, odd, or neither. Functions with this kind of symmetry are even, functions with this rotational symmetry are odd, and there are plenty of functions out there that don't really have any kind of symmetry at all, like this one. Right, if I spin it around upside down, that point's going to be lower than it used to be. It's not the same on the left-hand and right-hand side. That function is neither even nor odd. All right, so I want to use the algebra test to determine whether these functions are even, odd, or neither. All right, well, I'm going to replace x with minus x. If I get the exact same thing I started with, that's an even function. If I get the exact opposite thing that I started with, that's an odd function. And if I don't get either of those, that's neither. That'll be a function that doesn't have either kind of symmetry. All right, so here I'm going to play that game where I like to think about functions like this, right? I plug something in, that something gets cubed minus 6 times that something, and the algebraic test is to replace x with minus x. Well, when I cube a negative, I get a negative, so that's minus x cubed. Negative times a positive, that's plus 6x, and what I realize is this is the opposite of what I started with, and I can actually see that by factoring a negative out front. I feel very confident that I can tell right here because both of the signs changed. But here I have a minus out front of the original function. This function is odd. Moving on to number 2, I'm going to do the same thing. And here I have to be careful because 2 of the signs changed, but this didn't. It's not exactly the same, and it's not exactly the opposite. In fact, if I try to factor that minus out front, right, if it was exactly opposite, I'd see the original function, that sign changed. All right, so here I have the idea that up here, both signs changed, so that's the opposite, that's an odd function. It's not exactly the same, it's also not exactly the opposite. This is neither even nor odd. This function doesn't have either one of those symmetries. Over here for number 3, let's replace x with minus x. If I raise a negative to an even power, well, I'd have a minus x times a minus x times a minus x times a minus x. Everything's going to work out to be positive. So I have 2x to the 4th. Plus 4x squared plus 7, and that is an even function. That's exactly the same equation that it started with. Nothing changed at all. All right, and I have one more, and this one's a little different. So I'm supposed to replace x with minus x. So I get a minus x here and a minus x here, and if I'm not careful, I might make the wrong conclusion. But what I see here is literally the original function with a minus out front. That is the opposite of the original function, and there's a difference here. Right, these guys, I'm adding a bunch of things. In this example, I'm multiplying. So that negative out front changes the sign of the whole thing, and this function is also odd. Let's just do one more example while we're here. So this will be number 5, and I'm just going to call this f of x. And it looks a lot like the last one we did, except for instead of x times that square root, it's going to be x squared. So let's replace x with minus x. And with those even powers, nothing happens. That's the exact function I started with, and that is an even function. All right, so that's how you tell if a function is even, odd, or neither. You replace x with minus x and you see what happens. You get the exact same thing you started with, and that's an even function. You get exactly the opposite of what you started with as an odd function, and you get something else, well, that's neither.